Hi everyone, welcome to Sims. In the previous class, we discussed regarding the Newton's first law of motion. That is, when the net force acting on an object is zero, the body will be either at rest or in uniform motion. Today we are going to learn about the Newton's second law of motion. Before going further, let us have a small discussion on the examples of Newton's first law of motion. Suppose we are playing carom on the carom board. Sometimes the striker gets struck below the coins. When we pull that striker gently with a jerk, the coins doesn't fall. That is because of inertia of rest. And even when the carpet, when we take a carpet and when we beat the carpet with a stick, we can see the dust particles coming out. Those dust particles come out from the carpet because of the inertia of rest. Now let us take another example. Consider a body of mass 5 kg, let us say. It is tied with the help of a string. Below this 5 kg mass, another string C is also tied. Now, my question is, what happens if we pull the string C at a sudden jerk? Let us consider this 5 kg mass is at the point B. Now, if we pull this string C with a sudden jerk, this part, the part between B and C of the string will get cut off. Suppose what happens if we pull this string C slowly, then it happens that the part AB of the string gets cut off. This is because if you give the sudden jerk, this part BC is initially at rest, it opposes that one, and which is called as inertia of rest. Now, let us go on for the discussion regarding the Newton's second law of motion. This Newton's second law of motion is defined as the rate of change of linear momentum. The net force acting on an object is equals to rate of change of linear momentum, that is delta P. Generally, the linear momentum we say P equals to delta mv. Let us suppose that the object is initially at rest whose mass is constant. Then this linear momentum can be considered as mv. According to Newton's second law of motion, now let us see the derivation here. F net equals to d by dt of mv. Here we come across the three cases where you never see in the other classes. Frankly, I am saying you people. That in the first case, let us say the mass remains constant. That is, we can take this m outside, then it is d by dt of v. The rate of change of velocity is called as acceleration. Hence, that is ma f net equals to ma. That means the net force acting on an object is equals to the product of mass and its acceleration. Now, let us take the case 2. Mass remains constant, the body moves, the body changes its speed. It's a very common example that we come across in our daily life. What happens if mass changes? How can we say? What is the example that we can consider is that suppose the water is running out of the pipe. That means the mass is changing with respect to time. Per second, the water that is coming out with the help of some net force. Here we can consider that water is coming out with the same constant velocity. Let us assume. Here, in the case 2, P equals to m into v, F net equals to d by dt of mv. In the second case, I said that velocity remains constant, then v equals to d by dt of m. That is f net equals to v into d by dt of m. And we have the case 3 too. What is that case 3? P equals to mv, linear momentum. Now what happens if both mass and velocity change with respect to time? For example, the rocket which we burn during Diwali festival, it changes its velocity, it loses its mass too. That's the best example we can consider here. Okay, F net equals to d by dt of P, that is d by dt of m into v. Here, as I said before, that both the mass and velocity are being changed. Then what is derivative of uv? U derivative of v plus v derivative of u. That is m into d by dt of v plus v into d by dt of m. This is the formula for net force, where there is a change in both mass and velocity. Now today we have discussed regarding the examples of Newton's first law of motion, and we have seen the derivation of Newton's second law of motion and its examples, and there are 3 cases. In the first case, here the mass remains constant, the velocity changes, then the net force is equals to ma, that is the product of mass and acceleration. In the second case, the velocity remains constant, the mass is being changed, hence F net equals to v into d by dt of m. In the third case, both mass and velocity have been changed, hence F net is equals to m into d by dt of v plus v into d by dt of m.